Recording in progress.
Today we'll be looking at memory cache mapping techniques. So welcome to this presentation on memory cache mapping techniques. We will explore how cache memory significantly impacts CPU performance and delve into the critical role of cache mapping in the overall memory hierarchy. Now, our focus will be on the three main mapping techniques, aiming to provide a clear understanding of how main memory blocks are mapped to cache lines. So what at all is a cache mapping? And why is it? It defines data placement. Cache mapping is the method that dictates how blocks of data from main memory are placed into the cache. This structured placement is essential for efficient data retrieval. It also reduces CPU read time. The cache stores frequently accessed data, acting as a high-speed buffer. This reduces the time the CPU spends waiting for data from slower main memory, significantly boosting performance of the computer. It also resolves data location. Mapping techniques determines precisely where to place new data or find existing data in the cache during the cache miss. That's where the data is found, or cache miss, where the data is also lost. It also structures memory. So both main memory and cache are organized into fixed size units. Main memory is divided into blocks, and the cache is also divided into lines or sets, enabling systematic data management. Now let's move on. We have flexible placement. So unlike direct mapping, fully associative mapping allows any block from main memory cache line. This completes flexibility minimizes conflict risks. Now, must search simultaneously. There is achieved using content and content addressable memory, which are parallel comparison of tabs. There is also replacement algorithms. When the cache is full and a new block needs to be brought in, replacement algorithm, which existing block to evict. So common algorithms include least recent use, that's the LRU, or first in, as also now. And complicity. This is where the requirement of a CAM and complex requirement logic leads to larger task size and more expensive complex hardware, which also can also increase cache access time. We also have highest hit rates. Despite the drawbacks, its primary advantages is the highest possible hit rates and minimal conflict costs, making it ideal for small critical cache like translation, look aside buffers. Okay, so we are done with that. Let's move to the next slide. Comparison of mapping techniques. So this is a table that shows the comparison of mapping techniques. As it says, we have complexity, we have simple, we have high complexity, we have moderate. So this, as you see here, under the complexity, we have speed, and it's very fast, and it is slowest due to research or the search part of it. It also is moderate. This, as you can see here, the comparison are made here from basic complexity to simplicity. and from its highly complexity to its traits. So let's move. So the choice of mapping technique is a critical design decision, heavily influenced by the desired balance between performance, that the heat treats, the latents, and implementation constraints. So that's the hardware and the complexity, hardware complexity and the cost. So there are also practical considerations and examples, just as you see there. We have direct mapping, which we have fully associative critical buffers, set associative dominance. Algorithms are tools also, and design interdependencies. So under each, you can clearly see, let's take direct mapping image, for example. Direct mapping image is often found smaller cost-sensitive caches, especially those that are highly optimized for speed, where conflict processes are less problematic due to the specific access practices or small data sets. So under the fully associative for critical balance, due to its superior hit rate, fully associated mapping is typically reserved for all highly critical caches, such as deflation, look-aside buffers, which stores recent translations of virtual to physical addresses. You also, under the self-associative dominance, modern CPUs widely adapt such systems that the self-associative caches as various levels, such as level 1, level 2, level 3. This is because they offer the best compromise between performance, hardware cost, and complexity for general computing workloads. And under the algorithms keys for associative and set associative caches, the efficiency of the replacement algorithm. For example, let's say the LRFI is paramount. It directly impacts the cache's ability to retain frequently used data and thus the hits ratio. So design interdependence is also another point. So beyond mapping, factors like cache size, block size, and the degree of associativity are all intertwined. Optimizing these parameters is crucial for maximizing your cache hits ratio and minimizing memory access dangers. So in summary conclusion, let's take these key points. Cache mapping is fundamental for efficient CPU memory interactions, bridging the speed gap between processor and main memory. We explored three primary techniques, which were direct, fully associative, and set associative map. Each technique presents distinct trade-offs in terms of hardware complexity, access speed, and cache hit rates, dictating their suitability for different applications. A deep understanding, we also got a deep understanding of these mapping techniques, which is essential for optimizing cache. Consequently, overall system. We end this presentation.